In this video, we're going to look at a special example of constant acceleration. That is basically what happens if you drop something and it falls due to just gravity alone. We're going to call that free fall. So let's define the idea of free fall. It's basically what I just said. When you have something in free fall, as physicists, we assume that the only force acting on that object is gravity. Now, we know that in actuality, that's not totally true. There's going to be some air resistance truly. But here, what we often say is the air resistance is negligible, or it's a negligible air resistance. What that means is not necessarily that there isn't any air resistance, but it's just not going to make a big enough difference to change all of our numbers. So we're going to make a big assumption here and say there's no air resistance at all. So if this is a 2 kilogram ball, it has a force of gravity that we can calculate as 19.6 newtons. Free fall is an assumption where the only force is gravity. So let's look at what that does to our actual motion. If I have two objects, a 2 kilogram object and a 5 kilogram object, I can figure out what their force of gravity is. That force is the only one. 2 times 9.8 is 19.6. Now I also know that force is equal to mass times acceleration. This is a net force, but if this is the only force, it is the net force already. And I can rearrange that and say the acceleration is just the net force divided by the mass, 19.6 divided by 2, we're back at 9.8 meters per second squared. So this 2 kilogram object, if I drop it, should fall at an acceleration of 9.8 meters per second squared. Let's do the same thing for the 5 kilogram. Here I've got a larger force because 5 times 9.8 is 49 newtons. This 5 kilogram ball is going to experience more force of gravity. And we are used to more force being more change or more acceleration. But in this case, since the mass is also changing, if I rearrange that and say F over m, 49 over 5 is also 9.8. So it doesn't matter what the mass of the object is. All masses accelerate towards the Earth at the exact same acceleration if there is no air resistance in play. And this is where the physical, like physics idea of this might diverge from reality and what we experience. We are used to light things taking longer to fall sometimes because air resistance is going to have a larger impact on them when we calculate the net force overall than heavier objects. So for now, let's just assume that all of this is in free fall. If that's the case, then we're going to say that this downward direction being negative means that our acceleration is actually a negative 9.8 meters per second squared. That's going to get kind of annoying as we go through it. But in this video, I'm going to be consistent with that and say up is positive, down is negative. In this case, acceleration is negative 9.8 to match our directions. So let's factor in a couple of the scenarios that you might commonly see. Each one of these, I'm not going to put any numbers to it. We're just going to talk about if this is the setup, what do we already know just from the setup? If I drop something, you'll notice that it's under free fall. And the moment I let go, it's not moving yet. It accelerates from rest. So the moment I release it, its velocity is 0. It is a common misconception to then say, oh, it's also 0 at the bottom. In this case, it is not. We are assuming that this SUVAT, this constant acceleration, only happens in the moment that the ball is in free fall. So the moment I release to the moment it hits the ground. It hits the ground with a final velocity. It's the impact speed, not 0. Once it hits 0, other forces have factored in. So we know the initial velocity is 0. But we don't know what the final velocity is. And if it's in free fall, we're going to assume acceleration is negative 9.8 meters per second squared. There might be other values that we can get, but these are the ones that come from the scenario. All right, let's imagine then I throw a ball up in the air. It goes to the top and turns around and it comes back down. Now, in this problem, there's an important value for the top. We know that at its highest point, it comes to a stop before it turns around and accelerates back down to the earth. We want to access that velocity. That isn't the initial or the final velocity of this motion. The motion started at the hand and it ends basically at the hand. So the only way we can access that 0 is if we cut this in half. Basically look at just the first half or just the second half. If all I'm looking at is the first half, my final velocity is 0 because the motion starts in my hand and it ends at the top. And the acceleration is a negative 9.8 meters per second squared. This is another common misconception. It feels weird that the acceleration is negative even though the object is moving up. I will remind you that what a negative acceleration means in this case, if my velocity is positive and my acceleration is negative, acceleration is counteracting velocity, causing it to slow down. If I look at the second half of the problem, now we are moving down. I'm starting at 0, so now my initial velocity would be 0. And my acceleration is still a negative 9.8. Now I have a negative velocity and a negative acceleration. They are in the same direction, and it causes it to speed up. So that is important that acceleration is negative the entire time in both of these cases. All right, our third major scenario is what if you are up at a higher height and you throw it downward? Give it a constant velocity or an initial velocity, rather, going down. Well, we can't assume 0 in either of the locations. Now, the only thing we know for sure is that acceleration is still negative 9.8 meters per second squared. I give it an initial velocity, but then it's going to keep speeding up from there at that rate of negative 9.8. All right, let's look at a couple examples. For these examples, we're going to use these kinematic equations and our SUVAT variables and use the equation that matches the variables that we have. So let's start with a classic example of dropping a marble off the Empire State Building. Empire State Building is about 380 meters tall. How fast will the marble be moving once it hits the ground? For a free fall problem, it often feels like we don't have enough information. A lot of the information is going to come from the scenario itself. The only number I'm given is it's 380. Um, and I'm trying to figure out how fast it's going once it hits the ground. So I'm trying to find the final velocity. I know that it's going to start from 0. This is dropping it off the Empire State Building. So the moment I let go, it's 0. I know that the acceleration is negative 9.8 meters per second squared. And then the only number it gives me is 380 meters. Meters goes with displacement. So I'm going to put that in for S. If I look at my kinematic equations, I don't have time here. The only one that doesn't use time is v squared is equal to u squared plus 2as. If I plug in my values, solving for v, I'll get v is the square root of 0 squared plus 2 times negative 9.8 times 380. If you plug that into your calculator, it will give you an error. The error that it's giving you is because you're trying to take a square root of a negative number. So this is our first time that the negative is going to be really annoying to us. That negative 9.8 means that it's accelerating downward. If that is true, if down is negative, then our 380 also has to be negative. Here's why. This 380 in the problem tells you how tall the Empire State Building is, but the motion of the marble is that it starts at the top and it ends at the bottom. It is moving downward that entire time. Displacement is a vector, and vectors have a direction. So we're going to add that negative into our equation. Now the negatives will cancel each other out, and you end up taking the square root of a positive, and it gives you a value. Now I've written here negative 86.3 meters per second. The value it will give you is actually going to be positive. But in this case, if we're being consistent again with our directions, down is negative. If this marble is falling off the Empire State Building, it is going to be moving downward. So let's call it a negative 86.3. Now, that might feel annoying. There are a couple of things that we can do to handle that. One is technically you could change your directions. You could say down is positive and up is negative. That always feels weird to me, but it would mean that all of our values would be positive and it would ultimately give you the same thing. The other reason that you shouldn't be too worried about this is what this is actually asking, how fast, is often interpreted as a speed. And most of the time, the problem will actually be explicit and say, what is the speed in which it hits the ground? In that case, you're not going to present it as a negative. And honestly, most of the time, like negative feels weird. If I asked how fast does it hit the ground and you said negative 86, that would feel like an odd answer. So we are just typically going to give the magnitude. Um, if you don't have the negative, it's not a big deal in this particular case. We are still going to use the negatives in our problem because sometimes it does factor in and make a major difference. Let's look at another problem. What is the vertical velocity of a basketball required to reach the rim of a basketball hoop 3 meters high? This is an example where you throw it, and then we're essentially ending our problem at its highest point. We know we are trying to find the initial velocity, and at the highest point, it comes to a stop. So we're going to say v is 0. We know that we have a height of 3 meters, and then even though it's moving up, our acceleration is again negative 9.8 meters per second squared. Here, if you don't have a negative 9.8, it might actually give you an issue because we're going to use this equation again, and I plug in these values, and I get 0 squared is equal to u squared plus 2 times negative 9.8 times 3. I will multiply that, bring it to the other side, and take the square root, and I'll find that u is a positive 7.67 meters per second. Again, in this case, if you didn't have that negative 9.8, you would have the other issue that you'd be taking a square root of a negative without it. So just know and understand what that negative is representing. You'll get more comfortable with using it the more examples that you try. All right, let's look at one more example here. You flip a coin and you catch it. How high in the air? It is in the air for a total of zero point 0.6 seconds. How high did it go? All right, this is a classic up and down problem. In this scenario, we are trying to find S. If I use the entire motion, I would be starting and stopping in the same spot, which actually is a displacement of 0. So the only way I'm going to get S, how high, is if I split it in half. I'm going to say that A is negative 9.8. Up at the top is 0. So let's call U 0. We'll look at the second half of this problem. And then my time is the time it takes to go up and back down, which means if I'm starting at that 0 at the highest point, I'm not looking at it for the full zero point 0.6 seconds. I'm just going to look at the second half. It goes up 0.3 and down 0.3. It's a nice symmetrical motion here. So I'm going to use 0.3 as my essentially half the hang time. And then I am going to use this equation. S is equal to ut plus 1 half at squared. That ut doesn't really matter because u is 0 in this particular case. And then I plug in 1 half times negative 9.8 times 0.3 squared. And I get 0.441. Technically, if I were to do this, I broke my own rule. It should say negative 0.441, but I've already changed it to match what the question is asking. If somebody said, how high did it go? And you said, oh, it went negative 0.44, that doesn't really answer their question. It would be a negative technically in the second half of the problem because it's moving down 0.44. But then I want you to be able to interpret that and say, well, that actually means it's 0.44 meters high, about 44 centimeters up there. Now, I want to point out one other thing. If I chose the first half of this problem, you could totally do that. It would work. You would end up with a scenario that you don't have u, and there is not a kinematic equation that's given in the IB curriculum that doesn't use u. So you would have to solve for u and then plug it in and use it from there. So kind of sidestepped that problem and looked at the second half because you could do either. Either of them would work. So in this video, a fast look at free fall and some of the hidden values. You should be able to identify this constant acceleration and then find these hidden values and know how to use them in a kinematics equation and then use those equations to solve for an unknown with free fall.